Hello everyone, this is Mrs. Denton, and in this video we are going to study, really it's a review of how to find the area of two-dimensional figures. This is a lesson that you have studied throughout your math background. You visit it in elementary school, you see it a whole bunch of times in middle school, and here it is showing up again in geometry, but it's absolutely a fundamental geometry concept. So here we're trying to find the area of, on this first page, we're working on rectangles and squares. But before we do that, let's make sure that we understand what we're finding. Area and perimeter help us measure the size of two-dimensional shapes. So if we want to find the area of an object, we're really measuring the length and width of that object. And together, this measures how much space the object takes up. Or the space that the object covers, we'll say. It's describing how big the object is in a two-dimensional way. We definitely measure area in squared units. And that squared value matches the length and width, the two-dimensional aspect. So examples might be feet squared, inches squared, yards squared, and so on. Something squared. So the two shapes we're starting with are squares and rectangles, and I pulled these pictures right off of your SOL formula sheet, so there's nothing here you have to memorize. For a square, the perimeter is 4 times one side length, and hopefully that makes sense because we know in a square all the sides are the same. So if one side is 3, then all the sides are 3. And then the area is a side length squared. Let's try that here on number 1. This is a square. Okay, and if this is a 6-foot measure, then all the sides are a 6-foot measure. And to find the area, the formula is a side value squared. So we would take that 6, plug it in, and square it. 6 times itself is 36. And since we are measuring this value in feet, this would be 36 squared feet. 36 squared feet. So that could represent, let's say you have a room that's a 6 by 6 foot room, kind of a small room, and you wanted to put some carpet down in that room. How much carpet would you need? Well, you would need 36 squared feet. Okay? All right, let's compare this square to a rectangle. A rectangle is a little different because all 4 sides aren't the same. Instead, the opposite sides are equal to each other, but not all 4 sides. So for the perimeter, I hope it makes sense that you would add up the 2 lengths, 2 times length, and then you'd add up the 2 widths, so 2 times width. So the perimeter is 2 times the length plus 2 times the width. For the area, the formula is area equals length times width. So as long as you have a length value and a width value, you can find the area. So let's practice here with example 2. I would call 5 kilometers the length and 3.4 kilometers the width. So the area is length times width. So if we put everything in the right spot, that'd be 5 for the length and 3.4 for the width. Now this is definitely something we can do on a very basic calculator, so I just have my phone calculator here. 5 times 3.4 is 17. So the area of this rectangle is 17 kilometers squared because we're measuring in square units. All right, let's take a look at example 3 and 4. We've got something added in here that's going to take a little bit more of our geometry skills. Okay, example 3 is another square. So we know all the sides of the square are the same. We're asked to find the area, and the area formula is one of the sides squared. This 3 does not represent one of the sides. It represents that diagonal piece. So we're going to have to back up a minute and use something we previously know. And if you check out this picture, I am going to highlight one of these right triangles. And something I know about right triangles from our previous study is that the Pythagorean theorem can apply to a right triangle. So if we've labeled this S for side to match the formula, the Pythagorean theorem is a squared plus b squared equals c squared. Well, here, a and b are the same. They're both s. So that would be the side squared plus another side squared equals 3 squared. Well, it's lucky for us that these are like terms. Side squared plus side squared, you could put a little 1 out front if that helps you add them together. 1s squared plus another s squared is 2s squared. 3 times itself is 9. And now I need to solve for s. So I'm going to divide by 2 first. 9 over 2, you could leave it a fraction, or you could turn it into a decimal if you'd like to. That's 4.5. And then to get rid of the square, we would need a square root. So our side value is whatever the square root of 4.5 is. And again, I think my standard calculator here will handle that. I have to turn it sideways. Okay, so 4.5 square root. Oh, try again. Square root of 4.5. A little more advanced than I thought. All right, so I've got 2.12132, blah, 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 blah. Very long decimal. So about 2.12. Okay, so all of that was work just to figure out what the side is. Now I need to take that value and put it back into my area formula. Well, this is going to be pretty easy because we just took the square root of 2.1213, blah, 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 blah. So to square it back would just go back up a step. So my area here is 4.5 inches squared because I'm measuring in inches. Highlight that final answer for you. So we had to do a little work. We had to pull out the Pythagorean theorem, something we've studied before, in order to find the side lengths so that we could plug it in. Okay, let's try it again over here on number 4. I'm going to start by highlighting the right triangle. On this right triangle, I've got 6, which would represent the width, but I don't have a length. So I need to do some extra work to figure out what the length is because the area formula for a rectangle is length times width. So first things first, let me figure out what the length is. Got my Pythagorean theorem handy. 6 is going to represent A. I've got to figure out what B is. And C is 12, always the hypotenuse in the C value. All right, 6 squared. 6 times 6 is 36. 12 times 12 is 144. So to solve here, I need to subtract 36 from both sides. And again, that's definitely something your basic calculator can do for you, or maybe you could handle this in your head. All right, I'll get my calculator back out so you can see here. 144, take away 36, leaves me with 108. And now I need to take the square root of that value so that I can get B all by itself. So square root of 108. Whoop, not an erase. Square root of 108. I'm getting 10.39. Okay, so now I can take this B value back into the picture for the length, 10.39. Now I have what it takes to find the area of this rectangle. The length is 10.39 and the width is 6. And I can just use my calculator again. I'm not even going to round it. I'm just going to take that value and multiply by 6. And I get 62.35. And this is measured in centimeters, so I'm going to put on the tag centimeters squared. Okay, so we started out pretty basic. Up here in example 1 and 2, everything was given to you. All you had to do is plug straight into the basic formula from the SOL formula sheet. In example 3 and 4, it took it to another level. You had to find one of the missing values. We had to find a side and we had to find a length in order to use the formula. And then finally, in our last 2 examples here, we are given the area and we are asked to find a side value. So we're kind of working this one backwards. Number 5, we have a square again. All the sides are equal. So we could call all the sides S to match the formula sheet. Our area formula is A equals S squared. And this time we've been given what the area is. The area is 16 inches squared. So I'm going to put 16 in the place of the A in the formula, which is going to be a very quick solve for S. The inverse of squaring is square rooting. So if I take the square root of 16, I'm going to get 4. So this side is going to be 4 inches, not inches squared, because look, our area is in squared values. Our side length is in inches. That means I could pull out a tape measure and measure that as 4 inches, not 4 inches squared. Okay, let's apply those skills over here to this rectangle. In this rectangle, I would call 7 the width, and I'm trying to find the length. The area formula from the formula sheet is area equals length times width. They've given me 77 inches squared as the area, so I'll plug that into the A of the formula. I'm trying to solve for the length, and I've been given 7 as the width. So I've just done a whole bunch of substitutions here, putting everything into the formula, and it's a very simple algebraic solve. L times 7 equals 77. To get rid of this 7 or to solve for L, I'll need to divide each side by 7. 77 divided by 7 is 11. Now that 11 is measured in inches, not inches squared. Okay, that's our first set of shapes. If you'd like to pause the video here and do the the IXL practice to match while it's fresh in your mind, maybe that'll go faster for you. These IXLs, let me grab my sheet here. Okay, these are IXLs S2. Okay, so if you want to go ahead and get that taken care of while it's fresh, just pause the video and I'll see you in a minute. Okay, welcome back. In this next segment, we are going to look at parallelograms and triangles. And I've paired them together because truly, if you were just to take a parallelogram and split it in half, you would build a triangle. So I thought they went together. All right, let's take a look at this parallelogram. Our formula for a parallelogram is that the area is equal to the base times the height. And I like this picture that your SOL formula sheet gives you because the base is the same on the top and the bottom. So if they give you the top, that's still the base even though it's not on the bottom. And it's very, very, very important to understand that the height is the perpendicular height. And if you would just think about when you go to the doctor and they tell you stand straight up before they measure your height, that's how you would measure height. You would never measure height on a slant. In fact, that's called something totally different that we'll check out later. So our area formula here is area equals base times height. So we're going to start out simple again. Look at this first example here, number 7. Our area formula is the base times the height. Here we've got 7, which represents this base value, 7 feet long here. And 5, even though it's on the outside of the parallelogram, it's still at that perpendicular mark, which is very important. So 5 represents our height. So for our area formula, we've got the area is what we're trying to find. 7 is our base value. 5 is our height value. And now we just multiply. That we can do in our head. 7 times 5 is 35. We just found an area measurement. So this is in feet squared. We are saying that this strange shape called a parallelogram, it's like a slanted rectangle, covers up 35 feet squared. Okay. All right, let's compare it to a triangle. The triangle formula is really similar, very similar, except it's only half of base times height. And that's because if you could imagine the rest of the parallelogram here, you're really taking half of a parallelogram. So a parallelogram is base times height. A triangle is half of a parallelogram, so half of the base times height. So number 8 is a great example for a triangle. We've got 3 to represent the base, and 5 has been measured straight up on a perpendicular measurement, so 5.1 represents the height. So our area formula, area equals half of base times height. So our area will be equal to half of the base is 3 and the height is 5.1. Now, you can type this all in one giant string, or you can type it in multiple different orders. That is totally up to you. Got my calculator here. I'm going to type it in one giant string. Half, that's 0.5, times the base times the height. So all 3 numbers multiplied together give me 7.65. And that is the area of this triangle. That's how much space it covers. So we're not just measuring in linear inches, we're measuring in inches squared. Okay, I think those 2 first examples are pretty straightforward. In our next 2 examples, we may have to think a little deeper. Okay, take a look at number 9. We're back to a parallelogram in number 9. Okay, and our parallelogram has been twisted all around. So we have to discover where the base and the height are. So maybe you need to turn your page a little so you can see it. Okay, 20 represents the base. Now you've got 5 versus 7 here. 5 is what's measured on the perpendicular. So 5 is what represents the height. So 20 is the base and 5 is the height. Those pictures can get really complicated, so it's important we take our time to make sure we find what we're looking for. 7 is nothing. I'm going to cross that out. 7 is a distraction. So our area formula is base times height. We're solving for the area, so we need to put 20 where the B is and 5 where the H is. And maybe you can do that in your head. 20 times 5 is 100. And now we're a little stuck on the unit because it didn't tell us if this was inches or centimeters or feet or miles. So what we're going to write is that it's 100 units squared. Whatever the units are, inches, feet, miles, it would be in a squared value. Okay. All right, let's check out number 10. Again, finding the area. But we've got this triangle that's all twisted around. So if you need to turn your paper so that your triangle looks like the example, that could be a great idea. So it looks like I might need to rotate my paper. Okay. When I rotate my paper, 8 is definitely the base, and 3.7, there's that perpendicular piece, 3.7 represents the height. So 8 for the base, 3.7 for the height. Area formula of a triangle. Area is equal to half the base times the height. We've said that the base is 8 and the height is 3.7. Okay, again, I would recommend just typing this in all in one line. Then you won't have to worry about what goes where. So half times 8 times 3.7. That gives me an area of 14.8 measured in kilometers squared. So these two examples here in the middle, once you reposition the picture to make sure you can figure out what the base and the height are not too tricky. Number 11 is by far the trickiest, and that's because, again, it makes us pull something out of our brain from back in our previous study through geometry. Okay, so let's take a look. We have a parallelogram. Our area formula for a parallelogram is base times height. So this picture is set up very nicely. The base is here at 15. What's missing is the height. There is no height here. I cannot use the 8. The 8 is on a slant. That 65 is representing this angle measurement down here. So I can't use 65. So I have to take a moment to solve for the height. I've shaded this triangle in, to hopefully help you see what we're about to do a little bit better. Here we have a right triangle where we have an angle, the hypotenuse, but an unknown opposite value. Okay, so a few things we can use when working with right triangles. We can use Pythagorean theorem, a squared plus b squared equals c squared, which won't be helpful in this case. A squared and b squared are both missing. We only have c squared. And the other thing we can use with right triangles is trig. So this is an opportunity to use trig. So I'm going to highlight this triangle in another color here. The 65 degree is our angle of perspective. We've been calling that theta. Opposite of 65 is what we're trying to find. That's the height of this triangle. Opposite of this 90-degree angle is called the hypotenuse. I'm not using what's known as the adjacent side. There's nothing here that's important. So I've got to think back through my trig functions about which trig functions use the opposite and the hypotenuse. And jot this down as a reminder. So, ka, toa. All right, so ka, toa. We have opposite and hypotenuse, which uses the sine function. So we're going to use the sine function to solve for the height of this triangle. Let me write this out. Sine of 65 degrees is equal to the opposite value, which is what I'm trying to find, the height of the triangle, over the hypotenuse value, which is 8. Okay, if you remember correctly, we turned this into a cross multiply problem. So this would be 1 times h is equal to sine 65 times 8. Okay, now you're absolutely going to need a calculator for this part. Okay, this is my cell phone calculator, and it can handle this trig value. Sorry for all that reflection there. Okay, so I'm going to type in sine 65 times 8. Now in my calculator, I have to do 65 and then hit the, oh no, I don't. My calculator's so smart. Sine 65, close up those parentheses, times 8. Let's see, am I in degree mode? Yes, I'm good to go. So the height is equal to 7.25. 7.25. Now that was a lot of work just to find the height of this triangle. I'm not even done with this problem. Now my intention was to find the area, but I now know that the height in this formula is 7.25. So to find the area, I would need to put in 15 for the base value and 7.25 for the height value. And I can just finish this out on my calculator with a multiply. I'm getting 108.76 if I round to the hundredth. 108.76. Everything here was measured in inches. So this is inches squared. This is a great problem. It makes you really think through your options of everything that we've learned so far. I think you'll be seeing that problem again for sure. Okay, we're on to our last example for parallelograms and triangles. So this has been switched up a little bit. Look at what we're being asked for. We're asking you what is the base of the shape given the area. So let's look at that area formula again. Area is equal to 1/2 the base value times the height. Okay, we're looking for the base. We don't know what that is. We've been given the area as 15.4. So I'm going to put 15.4 in where the capital A is. I'm solving for the base, so that's what I don't know. And the height is 5.4. Okay, so there's different ways to solve this, and you may talk to different teachers and they'll give you different suggestions. I think what I'm going to do is go ahead and multiply half of 5.4, combine what I can combine over here. So 0.5 times 5.4. The left side is now 2.7 times b, which makes it really easy to get b all by itself. If this is 2.7 times b and I need to solve, I need to get rid of that 2.7 by dividing. So 15.4 divided by 2.7. And I am getting 5.70 for the b. And that is in inches, a measurement of inches, not inches squared. Because remember, when you're measuring a side length, you are not squaring that value. That is a linear value. So my final base measurement is 5.7. Okay, so we've seen a whole bunch of examples for parallelograms and triangles. I recommend, again, that maybe you pause the video and go do the IXL practice on it. I believe this IXL practice is the S.3. Okay, welcome back. I hope that was pretty easy for you. The next shape we're going to study is called a trapezoid. And here's your picture of a trapezoid from your formula sheet. A trapezoid has two bases, and that's what B1 and B2 are. B1, B2, they have to be two separate bases because you can tell they're different lengths. B1 looks short, B2 looks long. We also have a height in there again. And notice that that height is measured on a perpendicular line. So it's straight up and down. It's not on a diagonal piece. So area is equal to half of height times the sum of B1 and B2. These parentheses are going to be really important. So let's write this down. Let's try one here. Area is equal to half of the height of the sum of the two bases. Okay, so let's plug everything in. We're solving for area, which means we must have everything else. Half of the height is measured here on the perpendicular. So that's 2 times the sum, so we're going to add some stuff together, of these two bases. It does not matter which one you call B1 and B2. You could go B1 short, B2 long. It really does not matter. That's totally up to you. Maybe that's just an easy way to remember it. So B1 is 2.3 and B2 is 5.9, or the other direction. And if you've got a school calculator, this is going to be very easy to do. I'm wondering if my cell phone calculator can even handle it. Let's see here. So here's my cell phone calculator. I've got some parentheses here, so I think I'll probably be able to do it. Half is 0.5 times the height, which is 2, times the sum, so I'm opening a set of parentheses, of B1, which was 2.3, plus B2, which is 5.9. Close up those parentheses. So I've got half of the height and B1 plus B2, and I get an area of 8.2. 8.2. And that is 8.2 meters squared. I'm measuring in meters this time. So 8.2 meters squared. Okay, I picked this picture in number 14 because I thought it was kind of a funky looking trapezoid. So this is what we picture most trapezoids to look like, but this is also a trapezoid. It's just a trapezoid that's got like one kind of rectangular side to it. Okay, so got my area formula. Area is equal to half of the height times base 1 plus base 2. All right, and let's find everything in the picture. We're solving for the area. The height in the picture is the distance between the bases. So in this case, it's 5. And then again, you can pick what you call B1 and B2. I just tend to go short for B1 and long for B2, but it absolutely does not matter. So base number 1, I'm going to use 1.5. And base number 2, I'm going to use 5.1. And now I'm going to turn the work over to my calculator. Okay. Half times the height, which is 5, times the sum, so I need a set of parentheses, of adding the bases together. The sum of the two bases. I'm getting 16.5 for my total area. Area is equal to 16.5. This is measured in kilometers squared. Okay, so throughout this video, we have started out pretty easy. Started out with the very basics of the formula, plugging things in, just recognizing what's happening in the shape. And then we tend to amp it up a little bit. So let's see what's happening here in example 15. Okay. We are trying to find the area of this trapezoid again. So one more time, I like to write out my area formula so I know exactly what I'm trying to find. Half of the height times base 1 plus base 2. And let's see what we can find here in the picture. I do not see a perpendicular height. That is what is missing. I definitely do not have a perpendicular height. If I draw in some perpendicular lines, there's no way for me to know what that height is. So that is something that's missing, something I'm going to have to find. I do have two bases. I like to call base 1 the short base and base 2 the long base. There's nothing written in stone that says you have to do that. That's just how I like to do this. So I'm definitely going to have to pause for a moment before I continue because I don't have this full formula. I don't have the height. I have the bases, but I don't have the height. So I'm going to have to pause, do a separate set of work to figure out what the height is. Well, I am going to use this triangle to figure out what that height is. No wonder we had to study triangles first, right? Did all that work on triangles for so long, and here they are again. So I'm going to use this triangle here to find the height. we're back to a little bit of trig. We just did an example like this in our last little segment. In this triangle, I've got my angle of perspective. Oops, excuse me. My angle of perspective is 30. That's what I call theta. I'm trying to find the opposite value, which is the height of the trapezoid. And I've been given the hypotenuse of the triangle, which is 12. So I've got opposite and hypotenuse. This is another opportunity to revisit your trig functions. I've written down the 3 trig patterns over here: sine, cosine, tangent. Okay, and again, sine is what we're going to use because we're working on the opposite and the hypotenuse. So let's find that height. Sine of theta, which is 30, is equal to the opposite value, which is what I'm trying to find, that's the height of the trapezoid, over 12, which is the hypotenuse on my triangle. So I'm going to cross multiply. 1 times height and 12 times sine 30. Well, 1 times height, that's easy. That's just going to be h. The rest I'm going to need my calculator for. So I've got 12 times sine of 30. And I get 6. So the height of this trapezoid is 6. Now I've got to take that's 6 meters, because everything in this picture is measured in meters. I've got to take that and bring it all the way over here into the area formula. So this 6 came from our work with trig. Now I can finish it out. Get my calculator out again. 1/2 times 6 times the sum of the 2 bases, which are 16 and 22. I've got an area of 114 measured in meters, and area is always a squared value. Man, that is another awesome problem. Love it. Love that one. Makes you get some trig practice in, brings everything all together. Okay, I've got 2 more examples here for you. Let's take a look. In these examples, we are not going to be solving for area. Check it out. I've given you the area. What we're going to be looking for is a base in 16 and the height in 17. So let's look at this formula again. We've got area is equal to half of the height times the sum of the 2 bases. Now notice I didn't say you had to find base 1 or you had to find base 2. It really doesn't matter what you call these. I'm going to say I'm looking for base number 1 because that's the short one, and I tend to do base 1 as short and base 2 as long. The area has been given to me, 9.6. The height seems pretty easy to find here in the picture as 3.3. And I'm trying to find one of the bases, and I've been given the second base. Okay, it's time to get your algebra going now. I'm going to try to clean up this right side a little bit. Half times 3.3 is 1.65. Half times 3.3 is 1.65. Okay, I need to get this b all by itself, so I'm going to divide off this 1.65 first. Get rid of that first. So 9.6 divided by 1.65 is 5.818181. When I divided away that 1.65, the only thing that was left was b plus 3.9. Okay, so my last step would be to subtract that 3.9 from both sides. I still have the 5.818181 loaded in my calculator, so I just need to subtract 3.9. So I got 1.91818181. So I'm going to say 1.92. Now, when we're measuring the bases, that's not in miles squared. That base value is just 1.92 miles. That's a linear value. It's not a squared value because it's not an area. All right, we have one more to try. So in this last example on this page, we're finding the height. So let's look at the area formula again. Area is equal to half of the height times the sum of the two bases. We're told the area is 9.9. That's equal to half, and we're trying to find the height. And again, our two bases are listed here. I'm going to call base 1, 1.5, and base 2, 5.1. So now I need to use some algebra skills to figure out the height. I'm going to start in this set of parentheses. 1.5 plus 5.1 is 6.6. Then if I multiply half times 6.6, I'm going to get 3.3. Then to get rid of the 3.3 and get height all alone, I need to divide each side by 3.3. 9.9 divided by 3.3 is 3. So my height is 3. 3 whats? 3 kilometers or 3 kilometers squared. Well, remember, height is something that you would measure with like a tape measure or a ruler. So it's not a squared value, it's just kilometers. Okay, so if you look back through this lesson on trapezoids, you're going to see we started out very basic at the top. All we did was plug into the formulas. Example 15 here is super duper tough. You had to use some trig to find one of the missing pieces. And then 16 and 17 at the bottom, we are looking for something other than the area. We're given the area and we have to use our algebra skills to solve for a base or a height. You may want to stop right now and pause the video and go do the practice IXLs on trapezoids. Okay, on this last section of my video, we're going to talk about the area of circles and sectors. Off your formula sheet, we've got the area formula as pi times r squared, where r represents the radius, which is the distance from the center of the circle to the edge of the circle. I've also listed out the circumference formula, and we're going to practice that. Circumference is kind of like perimeter, but when we're talking about circles, we call it the circumference. And the circumference is equal to 2 times pi times the radius. Okay, so let's try example 18 here, and we're going to find the circumference and the area of this circle. The 4.4 represents the radius. So for the circumference, I'm looking at circumference is equal to 2 times pi times the radius. So if I take the 4.4 and plug it into the formula, I could multiply 2 times 4.4. 2 times 4.4 is 8.8. So 8.8 pi centimeters is one way to represent the circumference. This is called the exact value. So I'm going to highlight that because that is one way to answer this question. If I want to round it to a decimal, I can just use the pi button in my calculator here. So I've got 8.8 times pi. 8.8 times pi is 27.646, so 27.65. So there are two different answers here. We've got the exact value at 8.8, and then what we have is called the rounded value of 27.65. Both are good answers. The next thing I'm going to solve for on the same picture is the area, so I'm going to switch up my formulas. The area is equal to pi r squared. So to find the area, I would put the 4.4 in the R spot. Okay, and if I want an exact value, I'll have to find out what 4.4 squared is. So 4.4 times itself is 19.36. 19.36. So the exact area is 19.36 pi centimeters. Now we're doing area, so squared. If I don't need the exact value, that is a good answer. Sometimes my answers are written in this way with the pi still in the problem. If I don't need the exact answer, if I can round it, then I'll want to use the pi button in the calculator. So 19.36 times pi is 60.82. 60.82 centimeters squared. And that's not an exact value, it's an approximate value. We had to round to get that value. So there's two types of answers we're looking for here. Our exact answer is still going to have pi in it, and our rounded answer, we're going to use the pi button on the calculator. Okay, let's try again over here on example 19. We're looking for the circumference and the area. I'm going to switch up colors so that you can see my pen better. Okay, so for circumference, I'm looking for 2 times pi times the radius. In this picture, they've listed 12, which is not from the center to the edge. 12 is all the way across. So here we're looking at half of that value, which would be 6. So 6 yards is the radius. So when I plug that into the circumference formula, it would be 2 times pi times 6. All right, well, if I do 2 times 6, I'm back to 12. 12 pi. That is my exact circumference, 12 pi yards. If I want to get the rounded value, I'm going to need my calculator to do 12 times pi. 12 times pi is 37.69, so I'm going to round that to 37.70. 37.70 yards. Notice that's not yards squared. That is just yards because that's a linear distance, something we can measure with a tape measure. I'm highlighting everything in yellow is what's called the exact value, and that has pi in the answer. Everything in pink is my estimated or rounded value. So we've got exact answers and we've got rounded answers. You'll want to be familiar with both. Next, we're looking for the area of this circle. Okay, so back to the area of this circle. Area formula is pi times radius squared. So finding the area, and we're going to substitute in 6 for the radius. 6 squared is 36. So my exact answer is that the area is 36 pi yards squared. 36 pi yards squared. The rounded answer is where I'm going to need to use the pi button on my calculator. Okay, so clear this out. 36 times pi is 113.097, which would round up to 113.1. Area is 113.1 yards squared, and that's our rounded value. That's not an exact answer because here we're letting the calculator round for pi. All right, number 20 makes you think just a little bit. Okay, here we're not looking at a full circle, we're looking at a half circle, also known as a semicircle. So I wouldn't be calling the distance around circumference anymore. It's kind of circumference. And then we've also got this straight line. So Here, if I'm looking at half the circle, I'd want to take the circumference formula and cut it in half, because I'm only using half of the circle instead of the whole circle. So for a semicircle, we're going to be taking just pi times the radius. Just pi times the radius. So the radius in this picture would be half of this full distance. So our radius is equal to 22 inches. So the semicircle would be pi times 22, which would be easily written as 22 pi. But then that would be this part out here, 22 pi, which of course we could round and get my calculator ready. 22 times pi is 69.12. 69.12. That represents this curve along the edge out here, 69.12. To finish up the perimeter, I want to add in this extra middle piece here of 44. So 69.12 plus 44 is 113.12. 113.12. So the full perimeter would be half of the circle plus that 44-inch distance. Okay, finally I need to find the area of this semicircle. So to find the area of a full circle, the full circle area formula is pi r squared. But here we only have half of a circle, so I'm going to divide that by 2 for the semicircle. So pi times our radius of 22 squared, and take that value and divide it in half. Okay, I'm going to need to do a little bit at a time here. Pi times 22 squared. That's what squared looks like in my calculator. The numerator would be 1,520.53, and I want to take that and cut it in half, so divide by 2. I get 760.27. 760.27. Now, in this problem, it would not be worth my time to find an exact value, because we couldn't add something with a pi to something without a pi. So here I'm just going to write my final answers in a rounded format. Okay, let's switch it up just a little bit. Let's kick it up a notch. Circles are pretty easy. You just have your two formulas. Area is pi r squared, and circumference is 2 times pi times radius. Now what we're going to do is we're going to find just a little sector of the circle. So instead of finding the entire circle, we're going to find a little wedge. And to do that, we're going to take our area formula, which is pi r squared, and we're going to multiply it by this little ratio of the whole circle. So here, x is our angle measurement inside the circle out of a full 360 degrees. And then the second part here is we're multiplying this by our area formula for the circle. Okay, so x over 360 times the area formula. Let's see this example in number 21. First things first, I'm going to jot down my formula. Area of a sector is, I'm going to call it sector area, is equal to x out of 360 times pi r squared. This x represents the angle inside the circle. So here, x is equal to 51. That would be 51 out of 360 times pi times the radius, which is marked as 16, squared. Okay, I'm going to get an exact answer and a rounded answer. To get an exact answer, I need to do this in order of operations. I need to start with exponents. So 16 squared is 256. So that 51 over 360 stays a fraction, and the 16 squared becomes 256 pi. Now, I'm going to multiply the numerator together. So 51 times that 256. 51 times 256 is 13,056 out of 360. Now, chances are this fraction can be reduced. Okay, in my classroom calculator, it would reduce the fraction for me. Here, I think I'm going to get a decimal if I divide by 360. And I certainly do. I get 36.26666666666. So that's not really helping me when it comes to coming up with an exact value. It would help me more if I could reduce this fraction. So I'm going to pause the video and switch calculators. Okay, when I switched and used my classroom calculator, I typed this fraction in and it reduced it to 544 over 15. If I leave pi on the end, if I never use the pi button, that is called the exact value. So this is my exact sector area, and you're going to run into fractions a lot when you're doing sector area. If I want to turn that into a decimal, it's a very easy switch. I just type this fraction in, 544 over 15. Okay, do it here on my calculator, and then take that value and multiply by pi. So I've got 113.94 inches squared. So again, we can get our exact sector area before using the pi button, and then we can get our rounded sector area using the pi button. Let's get a couple more examples here. All right, in number 22, I always like to write the formula first. Sector area is the angle degree out of 360 times the area formula, pi r squared. So be careful here. I don't want to use 126. That's not my shaded sector. There's 360 degrees total in a circle, and the 126 is used for the white zone. So if I do a subtraction there, that would leave me with 234 for the gray zone. So I'm going to use 234 as my degree out of 360 times pi times the radius, which is listed as 13 squared. All right, so back to the calculator. Be careful here in your calculator. 13 squared is 169. So I've got 234 out of 360 times 169 pi. I'm going to multiply my numerators together. So 234, let's clear that out. 234 times 169, 234 times 169 is 39,546. 39,546 out of 360 times pi. Now, I'm going to switch calculators, and I'm going to let my classroom calculator reduce this fraction. Okay, in my classroom calculator, I typed this fraction in, and it reduced it to 2,197 over 20, and that is going to be my final sector area. So that is in yards squared. So my final exact shaded zone here is a real funky answer when you're looking at the exact value. I think the rounded value is going to make way more sense. So let me get my calculator ready. We've got 2,197 divided by 20. That's 109.85. And then multiply that by pi. Final area is 345.10 yards squared. So rounded value, 345.10 yards squared. I really think the rounded values make way more sense, but we just have to be ready to answer with both types. Okay, my final example here is an SOL example, so you can see what this might look like on the SOL. It says, Rodrigo planted flowers in a section of a circular garden as shown. What is the area of this section of the garden? So this formula, your sector area formula, is not on your SOL formula sheet. This is something we're going to have memorized. The pi r squared is on your SOL formula sheet. So you're looking for a section or a portion, that's what the x over 360 is, out of the total area. Here, the section is the 80-degree curve out of 360 times pi times the radius of 13 squared. So back to my calculator. We just did 13 squared a second ago in the previous example. So that would be 13 squared is times 169 pi. So if I type all of this in the numerator, 80 times 169 is 13,520 out of 360 times pi. If I divide that here in this calculator, I get a decimal that's not very helpful. So I'm going to pause, switch to my classroom calculator, and reduce this fraction. Okay, so when I type this into my classroom calculator, I get 338 over 9 pi. That represents feet squared. That's my exact area of Rodrigo's flower bed. If I needed it as a rounded value in decimal form, I'd just multiply those together. 338 over 9 is 37.5 continuing times pi. So I'd be looking for a rounded value of 117.98 feet squared. Okay, that was our last little segment here, and I know this has been a lot to practice, but there are a lot of formulas on this SOL formula sheet, so make sure you know what to do with your formulas before you start using them. All of these different IXL practices are practices on the various formulas that we've gone over within this video. So take your time, do one at a time maybe so that it gets kind of ingrained in your head. That very last one, U4, is all about sectors. So that one's going to be new and different for you. The rest of them I know you've seen before. So happy studying.